Okay, hello and welcome to this video on the basics of forces. You know, I was going to start this video off with a joke, but I didn't want to force it. Okay, here's what we're doing today. We want to define what forces are, distinguish between contact and action at a distance forces, describe forces as vectors and how they have units of newtons, and then apply the definition of weight to different planets. Cool. Okay. Let's get started. First, let's see a little bit of introduction about forces in football and rockets, right? Interesting comparison. Two fascinating things that have very different forces.
As NASA and football share the same city this week, here's a look at some of the same science principles they share as well. G-force is a measurement of the acceleration caused by gravity on Earth. This means, sitting on your couch, you're experiencing exactly 1 G.
There's liftoff.
Now, as a spacecraft accelerates up to more than 17,000 miles an hour, astronauts can experience a sustained acceleration of more than 3 Gs. But in short bursts on the football field, players can feel G-load impulses that are even higher. In fact, during a hit, a player can experience up to 10 Gs. That means for a split second, they can feel like they weigh as much as a full-grown bull.
3.
But when it comes to energy...
Okay, we'll hold off on the energy for now, but hopefully you caught the interesting part of that a football player can experience forces up to 10 times their weight. And so remember, weight is a force, and we'll go over this again. Weight is a force, so you can increase that force by going to a different planet, or in that case, being tackled, right? Being tackled can apply a force that makes you feel like you weigh 10 times as much as you actually do. Okay, so let's define forces. A force, that's a push or a pull resulting from the interaction of one object with another. So it's a push or a pull resulting from the interaction of one object or another. Nothing particularly fancy there. You kind of probably know these things generally in your everyday life. You've experienced lots and lots of forces, a push or a pull resulting from the interaction of objects. But now we're generally more interested in whether or not forces are balanced, And here's something that you should really try to take notes on and understand is whether or not forces balance has everything to do with whether or not their motion changes. So unbalanced forces change the motion of objects, whereas balanced forces don't. But that doesn't necessarily mean that they're stopped. It just means that they are not changing their motion. I know that's a hard concept sometimes, but not changing their motion. So for example, in this tug of war game, if both sides are applying 300 newtons of force in opposite directions, nothing's happening, right? The rope is basically still, but once one side is able to produce more force, you now have an unbalanced force, and the motion is going to change. They're going to go from being stopped here to starting to move in the direction of the team that has more force applied than the other team. Now, forces can be one of two kinds. They can either be contact forces, and that's when you actually physically are in contact. That's a literal push or a pull. Or they can be action at a distance forces. And those can happen even when objects are separated. And that sounds weird, but it's actually surprisingly common. It's happening all the time. So make sure you're taking notes on this. Pause the video if you need to. Here are some examples. So contact force, right? This boxer is punching this punching bag, and you can see that he is applying a force directly to the punching bag, and the punching bag is also applying a force directly to his hand, which is why he feels that punch. But now an action at a distance force is, for example, gravity, right? The moon and the earth are not touching at all. They're separated by almost 250,000 miles. And yet the reason the moon is going around the earth is because of this action at a distance force, the force of gravity. So the earth is this huge thing whose gravitational force can influence the moon. And of course, as you probably know, the moons can influence the earth as well. That's where we get our tides from. Okay, and forces are also vectors. So vectors, if you recall, that means they both have a magnitude, and a magnitude is a size or an amount, and they also have a direction that goes somewhere, right? So we represent them with arrows and with directions, right? So for example, this is a very bad drawing of a physics textbook sitting on a table. And gravity is pulling downwards on that physics textbook with 20 newtons of force. So that's a downward force, downward, right? Remember, we have to say where it's going. And it's not moving, so the forces must be in balance, right? If it was unbalanced, it would be shooting down towards the floor, but it's not. It's being balanced by an opposite force that's equal, pushing upwards from the table. So see the arrows showing the direction, the description has a direction, and then there's a magnitude or a size. Now the unit for force is the Newton. So capital N Newton, named for Isaac Newton. And so that's whenever we describe a force, we say it has a certain number of newtons. And newtons, remember, in the metric system, we can make units out of other units. So in the metric system, the newton is actually made out of a kilogram times a meter per second squared. And hopefully you remember that kilogram is a unit of mass. Meters per second squared is a unit of acceleration. So this is actually mass and acceleration together, which is going to come back when we see Newton's second law. But for now, just remember that we describe forces, including weight, with newtons. Okay, so let's review weight again. What is weight? It is not the amount of matter, which is what mass is. Weight is actually a measure of the force of gravity on an object, the pull towards something else of gravity on an object. And the metric unit for it is the Newton, right? Just like we said, any force uses newtons. We use newtons to describe weight in the metric system, and that's equivalent to saying what your weight is, or the weight of some object in pounds in the standard everyday American system. The thing is, there is no equivalent unit for mass in the American system. That's why it's confusing, because we say kilograms and pounds, but they're not actually the same measurement. Kilograms is a unit of mass, pounds is a unit of weight, but we can convert them very easily. And remember this really important point. The mass of an object is always the same. It's the amount of stuff in an object. And so long as that object is what it is, that's going to stay the same. But the weight of an object depends on the force of gravity on it. And when we're on Earth, we kind of ignore that, right? Because everywhere on Earth, we pretty much have the same gravity. But when you consider other situations, that does change it. And so here's the common example, right? So let's say your mass is 50 kilograms. On Earth, you would have a weight of 110 pounds, and that's what you're accustomed to, right? The force of gravity on your body results in a force of 110 pounds, and your legs are adjusted to that, and your legs are accustomed to pushing you around with that amount of mass, and our furniture is accustomed to holding that amount of mass, that amount of weight. But let's say you go on a trip to Mars. Notice your mass stays the same. Your mass stays the same, but suddenly your weight is less than half, because Mars has a gravity of about less than 40% of that of Earth. So that means you feel equivalently that much less weight. So you still have the same mass, but it'll actually be much easier for you to walk around. If you kept your earthbound muscles and bone structure and you went to Mars, imagine jumping, except that instead of pushing upwards for 110 pounds, you only have to push upwards for 42 pounds. And so you would get pretty sweet hops, right? Pretty sweet hops. And notice that in the metric system, we go from 490 newtons to 190 newtons, right? The weight is changing, the mass is not. The weight is changing, the mass is not. Okay, so hopefully that's a quick, easy introduction to both forces and the difference between mass and weight.